Welcome back to Mr. Baumgartner's chemistry class. So for this week's lab called Introduction to Gravimetric Analysis, we're looking at what happens when we start to mix solutions together. So far you've done stoichiometry where you can go from grams to grams. So you can measure out a solid, you know how much you're going to make during a reaction. We've done it with gases where we include Pivnert. But our next step in the process is looking at how we can do stoichiometry with a solution. When you've dissolved some kind of solid or some kind of substance in water, how do we use molarity in our stoichiometry? How does it fit into that whole thing? The solutions we'll be mixing together, and I'll just switch camera angles and show you in a second, are two relatively colorless solutions, one of potassium iodide and one of lead 2 nitrate. We're going to combine these solutions. They're going to make a precipitate. Then we're going to filter out that precipitate and let it dry for a couple days, although I started that a couple days previous to now so that we can just get it all in one video. And then you can play around with the stoichiometry and the math and see that this stoichiometry stuff we're doing is actually a real thing. All right, so make sure you've printed out your lab paper and, well, pay attention. If you got any questions or anything, shoot me an email. All right, the reaction we're going to be doing is between potassium iodide.
With the last name E through G, please report to the right side LC for testing. Freshman students with the last name E through G, please report to the right side LC for testing. Thank you.
All right, so we're going to be reacting potassium iodide with lead 2 nitrate. Potassium iodide is a relatively wimpy salt solution. I mean, you can get potassium iodide at the grocery store and add it to food. For those people who have like problems because they have too high a sodium, high blood pressure, this is just an alternative to salt. Whereas lead nitrate is a salt, but not an alternative to a salt that you could put on your food. That's definitely going to raise your risk of birth defects. Let's see, so we got potassium iodide, lead 2 nitrate. In this case, what we're going to get, if you remember from back in October, is something we call a double displacement reaction. The iodide and the nitrates are going to switch place, and we're going to get potassium nitrate and lead 2 iodide. Now let's see what's important about it. So we know that both of these were solutions. I showed them to you. They were colorless solutions. So I'm going to write AQ after them for aqueous. Potassium nitrate is also aqueous, but this little guy is going to form a solid. This is a solid that we'll see when we get a color change as soon as we mix these substances together. If you want to understand why some of these things are aqueous in solids, some of them are soluble, some of these salts, and some salts are insoluble, what you need to reflect back on is this little guy from early October. So if you flip over a periodic table where we have all of our equations and everything else, you've got those solubility rules down there, and you can look up things like sodium and potassium and nitrate and their relationship to lead to figure out when things are going to dissolve, be soluble, or when they're not going to dissolve, be insoluble. All right, well, let's go ahead and start this reaction out. I'll go ahead and do it in here. All right, first we'll add the potassium iodide to it. Exactly, by the way, I mean, I know you're following along in your lab sheet, but we are mixing 20.0 milliliters of 0.50 molar potassium iodide with, well, the same volume and concentration of lead nitrate. So you would think they're going to get used up at the same rate, but when you go through and balance this equation, which you should, when you balance this equation, you'll see that, well, the numbers aren't the same in front of these guys, and so that's going to cause them to be used up at different rates. As you'll see, potassium iodide gets used up twice as fast during this reaction as lead 2 nitrate. All right, so first we'll do the potassium iodide. Well, that wasn't too exciting. Let's try the lead 2 nitrate and see what happens there. Huh, that was more exciting. Well, it's going to be harder for you to see, but just in case you can't see, as soon as those two things came in contact with each other, we got a complete color change. And if you remember a color change in color. Yeah, I spelled color right. That's one of the many signs of a chemical reaction. And we also got a precipitate formed, which is another big deal. All right. So now what I need to do is I need to somehow get this precipitate out, because we are trying to do stoichiometry. Sorry about that. We're trying to do stoichiometry to see how much precipitate we've got. How many grams of lead 2 iodide did we make? All right, so how am I going to separate this out? Well, what I had people do in class, had a little cup and a little funnel. And we took a piece of filter paper, which is essentially a relatively thick coffee filter. And we turned this little pizza into a taco. Then we turned it into a quesadilla. And then we opened it up and turned it into a snow cone. Huh, look at that. That's called cooking. And then I'm going to try to transfer this little bit of awesome into here. And what will happen? Yeah, over the course of the next, I don't know, few minutes, is all the water is going to drain out into the bottom of the cup, and it's just going to leave the solid up here. Now, I would, if I was back there in the lab, I can't do it very well here, and I don't want to spray my computer, but I'd also be kind of spraying this with some distilled water, trying to wash as much of that down there into this little filter as I can to get the highest percent yield I possibly could. I'm not going to do that here, but it would be important that when we did that, though, that we used it with cold water instead of warmer water, because as you know, if you've ever cooked or done anything like that, warm water dissolves stuff, and we want this not to be dissolved. We want cold water in here just to make sure as much solid gets in this little filter as possible. And after about 3 days or so of setting here, what we would end up would be something that looks a lot like this. It's just a filter with a bunch of solid lead 2 iodide in it that we could weigh out. All right. So actually, I didn't walk up here with my lead 2 iodide. So let me go back there and get a dry sample that we can go ahead and weigh on this little scale. And we can see what our percent yield was. So we started out with 20 milliliters of each at that concentration. You need to do the stoichiometry to turn both of those things into grams of PbI2. If you struggle with that, in the chat for each class, I've posted a couple links to YouTube videos on solution stoichiometry, or you can just go to YouTube yourself and you'll want to type in solution stoichiometry. And that'll walk you right through it. All right, let me go ahead and run to the back so I can grab some samples here so you can get some data.
Freshman students with the last name H through J, please report to the right side balcony for testing. Freshman students with the last name H through J, please report to the right side balcony for testing. Thank you.
All right, I'm back. So what you would have got here for the stoichiometry, that would be your theoretical yield, the amount that you could actually make. Theoretical yield is going to be important when you do things like, well, percent yield, which equals how much you actually make, divided by that theoretical yield we get from stoichiometry times 100. That's certainly a question that you've got on your lab write-up. Another important thing we're going to do in here is your percent error, which is going to equal the absolute value of the theoretical yield. Again, you just got that a second ago when you did the stoichiometry, minus your actual yield, which we're going to get in just a second. So it's the absolute value. So just go ahead and make it positive when you get to the end, divided by the theoretical yield times 100%. All right, let's go ahead then and get our actual yield. So right here, I just ran back there and stole somebody's whose initials are SC and JB, or JAB. So whoever you are, thank you for donating to the cause. All right, so we want the mass of lead to iodide in here, but we certainly don't want the mass of the filter. So we're going to have to subtract that out. So here's an empty piece of filter paper. So my filter paper has a mass of 0.99 grams. And now I'm going to have to subtract that from the overall mass. So this is the mass of the filter with that lead to iodide. Don't eat that. So for my paper plus lead to iodide, that looks like that's going to be a mass, just in case you can't read it, of 3.71 grams. So I need to subtract that 0.99 out of there. That is going to give me my actual yield. And again, theoretical yield, that's coming from the stoichiometry. So that's all the data you should need for this lab. You should be able to complete the rest of that little guy based on what we've got here. If you have any questions or anything else, please shoot me an email, and good luck.